In this example, we're given a circuit that contains one capacitor and a bunch of resistors and sources. So it is a first order circuit because it contains only one capacitor in here. And what we can assume is that switch has been at position A for a very long time. And if you think about it, that means we have just this part of the circuit that was that is connected, or capacitor is connected to this part of the circuit. And after a very long time, 5 tau for this particular circuit, that capacitor will store some sort of an energy, and will have and it will have some sort of voltage across it. And the energy will be provided by that 50 volts. And at some sort of a time, we're going to call it time 0. This is basically where we're going to start everything. We're going to switch from A all the way to B in here. So what happens with B is this capacitor will start now interacting with this part of the circuit, because it will be part of this circuit now, because the switch is in B. Okay, so now the capacitor initially stored some energy because that 50 volt gave it some energy, and now it will interact with the 90 volt. So there's a couple of ways that capacitor will interact with that 90 volt. It will either give some of its initial energy to that 90 volt, or maybe it will take some energy from the 90 volt source, or from the whole circuit, not necessarily the 90 volt, like the whole circuit. Okay, and we'll figure it out using these equations. So what we're being specifically asked to compute is the voltage across that capacitor in here. That's what we're being asked to compute right before, like around the 0, basically after switching. I don't care about it I don't care about it before the switching. All I care about is like what was it after I waited for A for a very long time. And also we're being asked to compute IC of t, and IC of t appears in here. It is actually the same current flowing this capacitor when we connect that particular switch in here. So it's the current and the voltage across this capacitor. So let's get started. So what I will do is I usually start by saying, let me compute the amount of the voltage, basically the initial voltage stored. Well, I'm going to call it initial because I wanted to figure out what at T0, what was the voltage across this capacitor. And if we assume that the switch has been at A for a very long time, effectively I'm telling you, well, the circuit you have is actually this negative 50 volts in here all the way, and then we have the 15 kilo ohms, and then we have the 10 kilo ohms in here. Okay, and then what we have is we have this capacitor connected in here, and we know, well, basically I eliminated the A because this is what's happening. This is the circuit what we have. But we know eventually, basically, if we wait for a very long time, this capacitor will act as an open circuit because this source is a DC source, and the voltage across it, let's assume that this is here is the V0 that I'm after, or we can just say it's V at 0. Okay, VC at 0. Okay, it's the same thing. So the V0 is this particular voltage in here, and we can compute it simply here. So let me just write this. This is here before switching, before time 0, basically. Okay, so when t is less than 0. All right, so when t is less than 0, that's what we have. So we can compute the amount of V0, and V0, which is the initial voltage, VC0, or just simply V0. It's just simply 50 volts. Actually, it's negative 50 volts because the positive of the 50 volts is in here, and what we're interested in is the positive on the top. Okay, so it's negative 50 times 10 divided by 10 plus 15, and we can compute this value to be negative 20 volts. Okay, so we'll figure out right before switching what we have in here, and let me just highlight it. What we have across this capacitor between here and here, we have V0 to be equal to negative 20 volts. Okay, what does the negative mean? Negative means that the actual voltage, actually the positive, should be at the bottom, but we're going to keep it this way, just simpler. Okay, so we did this assumption, we're going to keep it this way, and I assumed it because this is the same direction as the VC of t, and it'll make things a little bit easier. All right, so right after switching, what happens? So I'm going to say, well, after switching, okay, what we'll have is we'll switch, this is switching. Let me just correct it. I think what I did in here, switching, okay? So right after switching, what happens right after switching? Right after switching, I'll have a different circuit. So let me just draw that. So the circuit I'll have a capacitor in here, and this capacitor will be connected to a 4 kilo ohms, and then it'll be connected to a 9 kilo ohms in here. Okay, this is 9 kilo ohms, and another 18 kilo ohms in here, and this one here is plus minus, and this is basically 90 volts. All right, and that's what we have right after switching. Okay, and I'm gonna just make sure to indicate this is a 50 microfarads, and initially it will have a voltage V0 to be negative 20 volts. That's what initially it has. All right, so what we have is now we're interested in figuring out what the VC of t in here is. Okay, we're also interested in what IC of t is here. It's the same current flowing because that capacitor and the resistor that is 4 kilo ohms are connected together. Well, what we have is these equations. We found out that these equations are the equations for step response of a capacitor. This is for the VC of t and the IC of t. I call them VT and IT, but they're basically for the capacitor. But what we do know is these resistors or these equations apply to a circuit that looks something similar to this. It will be like some sort of a voltage source, a resistor, and then a capacitor in series to each other, which is not the same as this circuit in here. So, because for example, which R should I be using? I have 1, 2, and 3. And the voltage source, well, the voltage source, I can technically use that, but anyway. So what happens is you shouldn't be using this particular circuit. What we need to do is we need to make sure that this circuit in here, and I'll just highlight, I'm going to just box it in this pink one in here. So this circuit has to look something similar to this particular circuit in here. And hopefully you have identified that this is just simply the Thevenin equivalent for that circuit. So what we need to do is we need to find the Thevenin equivalent of the circuit connected to this capacitor. So what I'm asking you to do is you take this circuit in here, which is this one here is 90 volt. Well, let me just do that. Well, I'll just draw it. 90 volt, and we have 18 kilo ohms. Okay. And we have 4 kilo ohms in here. And what we have in here is the 9 kilo ohms. And what we need to do is to find basically the Thevenin equivalent that we can see from here. All right, and this is straightforward. All we have to do is just basically go through the Thevenin equivalent and how to do that. So the first thing we need to do is, for example, we need to figure out what the V open circuit is, which is the same as the V Thevenin. So we can say V Thevenin is simply V open circuit, which is based on, well, technically there's no current flowing through this, so I can technically ignore this. These two are in series, so I can apply voltage division, the 90 volts, and I'm interested in the voltage across the 9 kilo ohms. So that becomes 90 volts times 9 divided by 9 plus 18, and that will be, let me just figure out what that value is. I think it will be 30 volts, okay? All right, so that's a Thevenin equivalent. What about the resistors or R Thevenin? So if you want R Thevenin, all you have to do is just basically we only have independent source in here, so I can either go through one of the three methods. I'll just basically go with the method will let me turn off all the sources in here. So I have an 18 kilo ohms, turning off a voltage source is replacing it with a short circuit. That's 9 kilo ohms, and that's 4 kilo ohms. And that means the R Thevenin that we can see from here is the following. It's actually R Thevenin is just simply the 9 in parallel with the 18 kilo ohms plus 4 kilo ohms, because the result will be in series with that 4 kilo ohms. And that should give me 10 kilo ohms. Okay, 10 kilo ohms. All right, so now I know the Thevenin equivalent. So now let me just redraw that circuit. So this voltage source now, what I have is I have plus minus. Instead of 90 volts, what I have is I have 30 volts. And then I have a resistor of 10 kilo ohms. And that basically is connected to the 50 microfarads in here. Okay, so this is the 50 microfarads. And what I'm interested in is figuring out that VC of t. And also it's the same IC of t. Remember, it's like it's the same current, so I just replaced it. Yes, IC of t is across the 4 kilo ohms, but it's the same current flowing flowing out of that capacitor, so we can do that. So now let me just make sure that I also indicate the initial voltage. This is V0, happen to be negative 20 volts. So now what I have to do is just basically go in here and just apply or use these equations with this particular circuit. So let me just move these equations down because now they apply to this circuit in here. Okay, so now what are we interested in? Well, what we want to do after switching is the following. I am interested in VC of t. What is the V of S? V of S in this particular case, it's actually that 30 volts. So we're going to substitute that with 30 volt. What's the V0? V0 happened to be negative 20. So again, we keep that negative because this is what we found out, okay? And because this is positive, this is positive, this is negative, this is negative, that's okay. We can, basically the V is the same direction as V0, so they have to have the same sign, but when they have the same sign, they will have the negative 20. What I'm saying in here is if instead what I did is I told you, you know what, the V0 happened to be negative in here, positive in here, and V0 happened to be 20 volts, you would have told me, well, this is negative, this is positive, and we'll end up with a negative in here anyway. Anyhow, we continue. So this one here is, I believe, should be negative V of S, which is 30 volts. E to the negative 1 divided by RC. We did not compute tau, so let me just compute that. So tau, which is just simply RC, it is 10 kilo ohms, okay, times C, which is 50 times 10 to the negative 6 microfarads. Okay, so we compute the microfarad to farads and so forth, and what we'll end up with is 0.5 seconds. And of course, 1 divided by tau is just simply 2, and that's second minus 1. Okay, so we can technically substitute the whole thing in here, -2, and then t minus t0, well, t0 just happened to be 0, and that's basically the equation. So let me just do the algebra. So that will be 30 minus 50 e to the -2t, and that's for t is greater than or equal to 0. And the unit for that is volts, okay, and that's Vc of t. And let's do a very quick sanity check. So let's assume that what happens is we know, because we know right before switching and right after switching, basically, the voltage should be -20. So let's substitute this t equals 0. If t equals 0, the whole thing goes to 1 in here. So this is 1. That means it's 30 minus 50, which is -20. So it's good right after switching, and before after switching is that way. And if you wait for a very long time, that t goes to infinity, that means the whole term in here goes to 0. So the final value would be 30, which makes sense, because if you wait for a very long time in this circuit, you will see that that capacitor will have 30 volts across it. We can now continue and compute the current flowing through that capacitor, which is IC of t. And there's a couple ways we can do it. We can either use the equation that we have already computed or we have figured out, or we can just simply say, well, we know that the current across a capacitor is just simply C dV of t divided by d of t. Okay, and of course this is VC of t. And if you take a look in this particular situation, the way we drew the current is actually hitting the negative port first in here. So we will have to put negative in here. And as it turns out to be that this equation, if you review where I covered it, it was in the case where IC of t was following passive sign convention and it was actually going to the positive side. So this one here, if you want to use it, which is the same as the other solution, instead of that negative, what you have to do is you have to tell me it's another negative in here. You have to multiply by a negative, which basically tells me that the whole thing here should be positive. That's what it tells me. Let me just make sure that here is positive. Again, the reason why we do that is because IC of t, the one that we computed this equation based on, we assumed that in terms of passive sign convention, the I is actually going to the positive side first. That's what we have, and you can go back to that video and you'll see this is how we computed that. You'll see that that IC of t was going to the positive side. That's what we did. Anyhow, let's either of the solutions is fine. I'll just use the equation because the equation is based on this one here, so I'll just basically go ahead and compute it. So what I'll have is the following. We have V0, which is -20, minus V of S, which is 30, divided by R, which is 10. I can basically keep it in kilo ohms, so that the result volt divided by kilo ohm will be in milliamp, e to the -2 of t, and that will become exactly -5 e to the -2 of t milliamps, and that's for exactly t is greater than 0, not greater than or equal to, because if you remember this equation in here, or this circuit, tells me right before switching in here, basically at t 0 minus, right before switching, the capacitor did not have any current flowing through it because it acted as an open circuit, as you see in here. But right after switching, things will start moving along and IC of t will have a certain value. So if I'm writing in here, what I can do is I can tell you, well, this IC of 0 minus was 0, but IC of 0 plus is not 0. We can compute that value actually by going in here, and I can tell you, well, IC, I'll just write it, minus is 0 milliamps or amps, and then IC of 0 plus, all we have to do is just go in here, substitute that by 0, we'll have that this to be 1, so the current that we have is -5 milliamps right after 0. So there will be a little bit of a jump between 0 all the way to -5 milliamp. So that's what we have in terms of the current. So we have now the equations for the current, which actually looks something like this, and we also have the equation in terms of voltage, which actually is something like this. We can go ahead and compute the power if we wanted. We can plot them. Maybe what I will do now is I'll just basically sketch some of these plots for you so that we can see what's happening. So here, what I will do is I'll tell you, well, here's my x-axis, which represent time, and my y-axis will represent actually both. It will represent the voltage and the current. I'll draw them both on the same diagram so that you can see them. So this will be t. So let's start with the voltage. So the voltage is actually this equation in here. You'll see when we have t is exactly 0, that means 30 minus 50 is -20. So we'll start somewhere in here. I'll just highlight it in red. That's basically -20, and that's basically for Vc of t, the one in red. And eventually, what we will have when t is actually infinity, the whole thing goes to 0. So eventually what we have is, this is -20 volts in here, and we'll have it going to all the way to 30 volts. So that's what it will have. So, and it will exponentially reach that. That's what will happen in here. So at some point, it will cross, the voltage will be 0. So at some point, the voltage across this capacitor will be 0. And we can compute it by just basically setting this to be 0 and figuring out what the value of t that will make it 0. You can go ahead and just compute that if you wanted to. Now, the other thing that I will compute, which is the current in here, and I'll highlight it in yellow. So before switching, right before switching, we were at 0. Okay, and right after switching, what happens is we got this particular value here, which is -5 milliamps. So let's assume that this is here -5 milliamps. Again, I'm basically doing this as I of t. So what happens, it jumps to the -5 milliamps, and eventually what we will see is if t goes to infinity, the whole thing goes to 0 because this capacitor will act as an open circuit. So you'll see it eventually basically goes all the way here and goes to 0. So this is how these two look like. Okay, so this is still a step response because the voltage across the capacitor jumped from -20 all the way to 30 volts. So it's actually a step response. So this 30 volts which was initially, we looked at it as a 90 volt, but because of the Thevenin equivalent, actually gives energy to this capacitor in here.